we are going to talk about image formation by lenses, and for the first little while we're going to do this by means of something called ray tracing. Before we can really do that, we need to start talking about what lenses are. Lenses have two major varieties, convex and concave, and this first video is going to be about convex lenses. A lens in general is just a curved piece of translucent, I suppose, material, and what we are going to do is make our lenses spherical lenses. A spherical lens just means we have a sphere and we are slicing a piece of this. Now if we do this, we're going to have something that looks like that. This side is convex and this side of it is flat. When we do these things in this course, when we deal with lenses in this course, we are going to be messing with double convex lenses. So they are going to look more like this, where both sides of it will have been cut from a sphere. So we're taking this piece and this piece and putting them together. A convex lens is a converger. And what that means is this. I'm going to switch and add these to my background because this time they'll be particularly helpful. So if I've got a lens like this, I'm going to mark a line that passes right through the center of my lens. This is called my principal or primary axis, or optical axis. Lots of names. Principal axis, or primary axis, or optical axis. All names for the same thing. You'll see it multiple different ways. If I have light rays that come in from really far away, those light rays would be traveling parallel to each other. So I have this ray that comes in, I have this ray that comes in, maybe I've got a ray over here that comes in, and these rays all hit my lens. Now one thing that's implied that's never really spoken too much is this. While we draw this shape as double convex, we are treating this as a thin lens. So we are treating this as like infinitesimally thin, meaning once you hit one part of the lens, you have hit the middle of the lens. What happens with a concave lens, with a convex lens, is this. These light rays that come in, they bend, they refract. And if I were to zoom in pretty far on this, I would see a surface that looks something like that, a light ray that's coming in this way. Here we go, we know what to do with this. I have a normal vector that points like this. I would have a continued path like this, but because I'm moving from air into glass, I have to bend toward the normal, so I'm going to bend up this way. Then when I hit the far other surface, I'm going to bend back away from the normal, but the normal has shifted directions, so what ends up happening is when I leave, I get a bending that looks like this, because in between here, I've got a surface like that. I'm exaggerating it. I've got a normal vector that points like that. And so I end up bending, instead of continuing straight, I end up bending away from the normal because I'm speeding up. Because this lens is infinitesimally thin, I'm going to treat this whole thing as though it happens at a point. I'm going to ignore what's going on inside the lens as far as this particular ray right here, this yellow ray, is concerned. And I'm just going to say my light ray comes in, hits the middle of the lens, and leaves at some other angle. I'm trying to line those up. So now let's see what happens with all these others. That's that ray. This ray is going to bend. This ray is going to bend. This one and this one. All my light rays bend. And what happens is these all meet up at a point over here. This point is called the focal point. When I said this was a converger, it's because it's taking these parallel rays and converging them into one, like all onto one point. So now, getting rid of all the dots because they become a distraction eventually, we have a focal point. We have these light rays converging. So a convex lens converges, which is reasonably easy to remember because I guess I could have grabbed the E also, because they start the same way. I said I've got a focal point over here. The distance from my lens to that focal point is called a focal length. And it gets the letter F. One last piece. We are cutting these lenses out of spheres. If I've got a sphere like this and it has a radius of, let's say R is 20 centimeters. If I cut this into a lens, this will produce a lens with a focal length of R over 2, or in this case, 10 centimeters. That's just how the focal length compares to the radius of the sphere that this is cut from. If you wear corrective lenses, the unit that you will have seen instead of a focal length is something called a diopter. This is like the power of a lens. And the diopter is just 1 over the focal length. So if you have, if you are wearing glasses that have a power of +2, if you wear glasses with a power of +2, what this means is that 2 is 1 over the focal length, so the focal length must be 1 over 2.00, and that would be in 0.50 meters, or 50 centimeters. A positive power lens means we have a convex lens. It is a converging lens, so we get this power of +2. We'll talk about negative diopters a little bit later. That's convex lenses, and then we'll run through examples of what to do with them and how they form images in just a little bit. Those will be the next couple videos.